I'm going to talk about microtomography and its use in appraising the macroporosity of biochar. So a little bit about my interest in biochar, just to give you some context. I'm interested in developing ways to functionalize or activate biochar to enhance absorption for cationic radionuclide species. I'm primarily interested in strontium, cesium, and uranyl. And I'm interested in how activation can tune the pore architecture for this application. I use Synchrotron X-ray techniques in order to examine pore characteristics and architecture, as well as binding mechanisms and things like this. So in the radioactive waste industry, ion exchange zeolites are already quite well established, but there are a number of limitations they have where they're, for example, not compatible with environmental systems, so they are fouled by organics quite rapidly. They generate large volumes of waste as well, which may not seem like an enormous deal, but when you consider the cost of radiological shielding and long-term geological disposal of radioactive waste, costs spiral quickly. And finally, the zeolites themselves can be very costly. So in contrast, biochar-based sorbents are far more compatible with environmental systems, making them far more applicable across a range of possible applications, such as in reactive barrier in situ type applications, cleanup of legacy sites, and in the case of accidental release as well. They're capable of going significant volume reduction steps for eventual long-term storage, either compaction, combustion, or further pyrolysis, which translates to big savings. This is actually a key metric in the nuclear waste industry, is volume of waste. And finally, of course, they're cheap and abundant. So, as you know, there are a whole host of uses of biochar, and this is multiplying all the time, really. One of the emerging issues as the uses of biochar becomes ever more high-tech is this issue of batch-to-batch consistency. So things like mineral phase composition and differences in porosity due to feedstock growing conditions and so on. As I said, this is most important in high-tech applications where variability can dramatically affect performance. And it's also really important in realizing small lab scale proof of concept type research into industrial and commercially viable products. This is certainly the case in my field of interest, where variability in performance will have long-term safety implications. So I'm interested in strategies that can mitigate the natural variability in biochar. And probably the most effective strategy to ensure uniformity is chemical activation. So chemical activator being simply a chemical agent which is mixed with biochar either before or after pyrolysis, and it serves a dual purpose of both enhancing the characteristics for end use and in reducing batch-to-batch variability as well. So the effect of activation on micropore structure is quite well studied already, but in terms of the macropore structure, it's far less well studied. And macroporosity is, in fact, quite an important feature for something like absorption. The macropore structure has implications for a range of reasons, affecting water retention and plant available water, nutrient movement, the effectiveness of their use as microbial niches, and most importantly for me, the kinetics of absorption and other processes which require transport to inner surfaces of biochar. Now, one of the key competitor materials, as I mentioned, are zeolites, and the macroporosity of zeolites is currently an area of big interest in zeolite research. They use this term hierarchical porosity to discuss how porosity across a range of orders of magnitude all have a part to play. As you can see here in these recent images, they're termed molecular highways, the larger pores, for facilitating transport to the macropores. I would argue that if biochar-based materials are to rival synthetic zeolites and other inorganic materials, this degree of pore size control and tunability via activation methods should be striven for as much as can be. And this is my motivation for studying the macropore architecture in activated biochars. Microtomography is a key technique for pore space analysis on this scale. And I'll show you some work on why I think that is. So for this experiment, I chose one key activator, which is commonly used, that's zinc chloride, as a sort of proof of concept type study to see if indeed the macropore structure was altered. So I chose a spent coffee ground feedstock, created a biochar, control biochar, and then the zinc modified analog to do microtomography on. In my case, I used a synchrotron-based X-ray source. There are lab-based X-ray sources for microtomography which work very well indeed. I'm happy to talk a bit more in the questions about why I'm using a synchrotron source, but I'll carry on for now. I will like to explain a little bit about a synchrotron because I'm not aware if everyone is familiar with it or not. A synchrotron is simply a type of particle accelerator that generates very bright light. In fact, it's something like several orders of magnitude brighter than the sun. Generally, the smaller the system you're studying, the larger the instrument, and that's certainly true in this case. The circumference of diamond light source here, for example, is about half a kilometer. The way it works is by accelerating electrons using magnets to relativistic speeds close to the speed of light. And by accelerating electrons through a magnetic field, light is given off, which is then used at the beam lines by users for spectroscopy and microscopy. And one of these uses, of course, is X-ray microtomography. So the setup for this is the sample is sat on a rotating pin, and it's gradually rotated in increments, and X-rays are shone at the sample at each rotation. The X-rays are attenuated by energy absorption in the sample and collected at the detector. The signals at each rotation are then reconstructed into images. It works in a similar way to a human CT scanner, you could say, except that in the case of a human CT scanner, it's the detector and the X-ray source which are rotating, since it's not practical to rotate a patient. That's the only difference, really. This is what the setup looks like at Diamond. X-rays coming in here. The detector sits on this plate here, and the detector array here. And the sample is attached in place with a magnetic pin, as you can see. The data output looks like a stack of multiple two-dimensional images, which are in fact oriented as though looking from above. That's why it's called a stack. That can then be used to reconstruct a three-dimensional volume, which looks a bit like this. That can then be viewed in a number of ways. This is the raw feedstock, the spent coffee ground particle, in false color, of course. Notice that the sides are quite planar. That's purely because the particle was larger than the field of view, not that the sides itself were so planar. So this is great for viewing objects with interesting outer structure, but for internal structure, not so useful. What's far more useful for biochar is to play through the two-dimensional images as though it's a video. So this is played at 20 images per second, as though you are moving down through the internal structure of the biochar. So the unmodified biochar first. Lighter is biochar and darker is pore space. As you can see, there are larger void spaces on the order of hundreds of microns. A sort of structure which, in my mind, is recognizable to a biological material is also present. Although, yeah, I'll just replay that, and I'll also play the zinc chloride modified biochar alongside. You can see that the biochar walls are significantly altered. They seem thicker, the pores seem smaller, and there are no large voids as is seen in unmodified biochar. So these images can then be further processed to yield more quantitative data. The way I did that, there are multiple ways to do that, but the way I have done that is a technique called thresholding, which involves setting a threshold value on a grayscale from black to white. The user can set a particular value, and then it's a trivial matter to count all of the pixels that are lighter or darker than that set threshold, which corresponds to one of two phases. So this image here, you can see that the lighter phase is biochar, the darker phase is the pore space. However, the contrast in the raw images isn't really good enough. While the human eye can discern the difference, you can see here on this histogram of grayscale that it's not possible to effectively discern between the two phases. So a filter can be used to enhance the contrast. This is a Paganin filter, which is done through an in-house program at Diamond. So you can see the contrast is much improved now. And if you look at the histogram, there are not two fully resolved peaks, unfortunately, but the resolution between the two is much greater. And you can see that there are two peaks present here on the grayscale, histogram grayscale. Then it's a trivial matter to set the threshold value in between the two, as you can see. And this red is a mask which is set upon top of the biochar, which is all of the lighter pixels, and then they are counted, and that will once that is done on a number of images, that will give you a overall pore volume. Notice that there is a error here, a radial error, that the biochar at the outer edges is not being correctly thresholded as it is in the center. But this error is the process of the data acquisition, and it can simply be removed by cropping to a central region. So this gives figures for overall macropore volume. As you can see, the feedstock has the least. The unmodified biochar has the most. When I first started processing these, I made the assumption that since the macropore volume of a zinc modified biochar is always greater than the unmodified analog, I thought that the macropore volume would also be larger. As you can see, it's not. Superimposing the images, the reason why seems to be that these large voids tend to open up, probably due to collapse of the pore structure during pyrolysis in the unmodified biochar. So in reality, this is consistent with the enhanced macroporosity of zinc modified biochars, because in the unmodified biochar, there are fewer internal walls and less internal surface area on which for micropores to form. which is perhaps why the zinc-modified biochar sees greater macroporosity. There are a number of other ways that the data can be numerically realized. It all tells a similar story in this case, that for the unmodified biochar, pore areas are bigger and larger. There are fewer pores per image, which could mean either that the pores are larger or there is a different degree of interconnectivity. I'm yet to fully get to the bottom of that. And finally, the ferret diameter, which is a sort of caliper diameter, or a measure of the largest, measure along the largest axis of a pore. And you can see that that is greater in the unmodified biochar on average. The ferret diameter can also be viewed as a distribution. So this is analogous to a pore size distribution, except it's along the largest dimension of each pore. Note that the scale here is actually quite different. In the zinc modified biochar, there are a much greater number of pores that are on the smallest scale at the limit of detection here, whereas there are a greater number of pores which are larger in the unmodified biochar, which again is consistent with BT gas absorption data, which indicate that there are a larger number of micropores in zinc modified biochar. So this is a image from a paper in 2014 by Catherine Brewer, in which she discusses biochar porosity. And as you can see, biochar pores span several orders of magnitude, and each size range is relevant to various environmental processes and biochar applications. The microscopy techniques scan most of these, but they're only able to view external surfaces, since biochar doesn't cross-section particularly well. Gas absorption analysis is blind to larger pores, although it's a key technique, of course, for smaller pores. Tomography as a technique is able to provide both qualitative and pretty detailed quantitative data. Now, this was in 2014, and the resolution for my data is already far enhanced than it was in 2014. There are similar techniques, nanotomography and tychography, that allow resolution down to below even 100 nanometers as well. Just to recap with these images, these are all tomography data on biochar, and in terms of pixel size, this has decreased in the past 5 years or so, as the ability to image at greater resolution is increased. As that has improved, as has computing power. To give you an idea, one of my samples, the data for one of my samples was around about on the order of 200 gigabytes. So the computing power to process just one of these samples is significant, and it's not always readily available. So computing power has been a barrier, and as computing access to high-powered computing increases, as does the image processing tools. There are, as I said before, many ways now to process tomographic data. So in summary, the macropore architecture parameters such as the overall volume, the tortuosity, the interconnectivity, has implications across a range of applications. In my case, I'm most interested in the kinetics of absorption. Chemical activation plays a key role for two reasons. It brings about greater batch-to-batch uniformity, and it allows some degree of tailoring the pore architecture. And finally, I think microtomography is really a key tool for looking at pore space characteristics on this scale, especially if one wants to tailor the pore characteristics in greater detail. Finally, a few words on future work. I was hoping to be back at Diamond to complete this work this summer and even perhaps present it today, but unfortunately the situation has changed all of that. So it's now in the future work section. I need to do some repeat measurements to ensure that these samples are repeatable. And I'd like to examine a wider range of common activators, of course, and then also examine the interplay between different biomass feedstock types with the activating agent. And that's me finished, if there are any questions.
Well, thank you very much, Stella, for your presentation. And if anyone has any questions, please just unmute yourself or write in the chat.
Yes, I have a question. This is Hugh McLaughlin from America. Could you comment a little bit about the method to introduce the zinc chloride into the sample? Was it prior to doing the pyrolysis step, and then the pyrolysis step was identical from there out? So just some insights as to how the sample's created. Thank you.
Sure, absolutely. It was pre-treated with zinc chloride mixed in a 1-to-1 mass ratio, dried, somewhat pyrolyzed as with the control sample, and then the zinc was, the biochar sample was then washed in, I think 1 molar HCl, and then water to sort of remove the zinc, any residual zinc there. Does that answer your question?
Well, answers always create questions. So the temperature of the pyrolysis was 375 C, I seem to note?
Yes.
In both cases?
In both cases, yes.
Okay. I think your future work will be very insightful as to the different starting material. Spent coffee grounds is an odd choice, although a readily available one around academic circles because of all the coffee drinkers.
Sure.
Excellent work, excellent work. It's amazing how much farther PhD research has come since the good old days when I got mine in '88, where we were making things out of lathing things and measuring them with burettes or something like that.
Well, I don't know if perhaps we're going to go back that way now with increased restrictions on movement, but we'll see. Anyway, thank you.
I would also have a small question. Why did you choose 375 degrees Celsius? Because that's quite low for biochar.
Absolutely. I think perhaps some people might argue it's not even really biochar at that low temperature. The purpose was these samples were part of a wider project which was initially attempting to functionalize biochar with zinc sulfide nanoparticles. And it's for that reason that I chose a low temperature pyrolysis. The tomography work at that time came secondary to the attempt to sort of modify the biochar with zinc sulfide, which didn't work. But the purpose of the low temperature treatment was in order to try and, I think, I can't remember the exact reasons why, but it had something to do with decomposition temperatures of the sulfur input I was using.
You got a couple of questions in the chat. So the first one was, do you think that the synchrotron method will become cheaper or standardized in future? Do you have any insights on that?
things are quite up in the air with synchrotron work at the moment because of the global situation. I don't really know how things are going to pan out in regards to that. In a wider sense, I really hope so, because there are a number of advantages that the Synchrotron X-ray source has over lab-based sources. For example, the tunability of energy and a much higher energy, which is much more important in my case when I might in future have high mass elements in my samples, radionuclides. I'd like to think it would be, but the fact that there are so few synchrotrons means that I think lab-based sources are bound to play an important role as well. Sorry, I can't seem to bring up the chat box myself while I'm sharing my screen. I can't work out.
I just read it out because otherwise in the video we won't see it anyway.
Okay.
Did you validate the results with another method of measurement?
Right. Yes, I did. I didn't present that because I'm unable to, with the way lockdown is at the moment, I'm unable to access the computer we have at Leeds, which is physically located in Leeds. I can't access that remotely. But using the same data set, I did a slightly different image analysis with a open source machine learning program called Elastic. That's spelt with an I-L, not E-L. And that, I believe it was originally created for biosciences for applications like cell counting, something like that, but it's excellent. I recommend it. It's very easy to get it to distinguish between two phases. As you saw in my images, the contrast isn't brilliant, but it does a great job. And I can't show you the data I have on that, but I verified that it was very similar to what I had shown you through this thresholding method.
And did you think about the mercury porosity as a similar pore size measurement?
This is a technique I don't know much about. I read that it works at a certain high pressures, I believe, and that there is a risk of crushing the biochar. Now I think perhaps with a more lignocellulosic feedstock, perhaps that's not so important, but with something like a spent coffee ground, I thought it might be a problem. But yes, I certainly would like to verify my results with as many techniques as possible, and hopefully I can do that in the future.
So I would say last question. Well, okay, let's take two last questions here. What might be the reason behind the decline in porosity volume on zinc chloride activation than that of unactivated ones?
It's in the lower pore volume, I think that's referring to, or the macropore volume, I should say. So I think that's because I obviously didn't do a great job of explaining this, or perhaps I rushed it a bit, but let me go back. So in the unmodified biochar, it appears as though the internal pore structure has collapsed somewhat into larger voids here, which means that the macropore volume is greater. Whereas in the zinc chloride modified biochar, these larger voids aren't observed. And I think that's the reason why the macropore percentage volume is greater in the unmodified biochar than the zinc chloride modified biochar. I'm happy to chat with people over email about this if I haven't explained anything very well.
And I would say as the last question that I give you from the chat, can this work be useful beyond radionuclides?
Well, I guess everything that I do applies to heavy metals, because essentially they're chemically identical. The only difference is the radioactivity, I suppose. So yes, for heavy metals, and I hope so for other contaminants as well. I'm also interested in redox electron donating and electron accepting ability of biochar. I did a bit of that when I did my master's. So it'd be curious to, I'm curious to study things like degradation of organics as well. And in terms of pore size tuning, that could be a very interesting facet there, with organic molecules sometimes being a lot bigger.
Okay, thank you very much, Stella. I think we closed the first presentation.